You all, I am sorry that these things keep happening. It's unfortunately one of the few things I can't promise you all is that things will work the way they're supposed to. Ain't that a lesson for life? Things only work so well for a certain amount of time. We had such a good run too. Technology was doing so well for us for so long. But better at the end than I guess any other time. All right, great, we're back. Hello on people, sorry for the delay. So, look how snappy that is. Wow, feels like going from dial-up to cable. So we have our object distance is 2 meters. Our focal distance is -1 meter because it's a diverging lens. Solving for distance to the image equals question mark. The equation, and this one doesn't have my sweet, sweet new answer. Let's just go ahead and do a new question. I'll delete the old one. Y'all can pick the right answer as I give it to you. Great. So 1 over F equals 1 over DI plus 1 over DO. We are solving for DI. So remember I told you all, I'll work it through again. 1 over DI equals, let's make this a little easier to read, equals 1 over F minus 1 over DO. And then at the end of the day, we just do 1 over everything. 1 over F minus 1 over DO. Now, the thing that's different about this one versus the last one, that's a little hard to read, so let me scoot that around. The thing that's different about the last one is that my focal distance is negative. That's the reason I asked two questions that looked almost identical. The only difference here is F is negative. So when I plug in the numbers, DI equals 1 over 1 over 1, but that's negative, minus 1 over 2, which comes out to -1 minus 1/2 comes out to 1 over -3/2, which ends up getting flipped to -2/3. We return that negative, so there you go, make certain you answer D. If you don't, I don't know what to do for you. We get a negative image distance. It's a diverging lens. I told you all, diverging lenses always give you a negative image distance. Ta-da, that emerged in the math. No extra step was necessary to get there. So this problem doesn't really have any trickery to it. You just basically have to make certain you know that the focal point is negative, and then everything else is the same. It's the exact same problem as the last one. If I go backwards, my step 3 looked identical. They look absolutely the same. All I did was change it from 1 over 1 to -1 over 1. But the answer comes out drastically different. Previously, the answer was 2 meters. Now it's -2/3 meters. So small change obviously makes a big difference. But, I mean, this wasn't a small change. The reality was this lens looks like this, and the converging lens looks like this. That is a pretty significant, so mathematically it's a small change, but the reality of the physical situation, they are quite different. Completely different shapes. And yeah, if you're getting contact lenses, you better have the right shape, otherwise it's not going to do what you want it to do. All right, so fairly straightforward there. While we're sitting here, let's just make up another clicker question on the fly, because we enjoy doing that. Clicker question. So, in the previous problem, DI equaled -2/3 meters, and DO equaled 2 meters. Make certain I'm not lying to you all. Good job, me. What will the magnification be? So this is going to be a throwback, kind of look through our stuff. What will the magnification be? And let me make certain I'm careful here and give you all the right answer. Will it be -1 over 3 meter, or -1 over 3? Magnification has no units. Will it be +1 over 3? Will it be, let me do every possible permutation. That's kind of funny how that works out. Will it be 3, or will it be +3? Oh, this is a new question. Oops. Stop. Hopefully you didn't answer this one on the old one. If you did, whatever. I'll go back and just give everyone the points. Life will be good. In the previous problem, di equaled negative 2/3 and do equaled 2 meters. What will the magnification be? So taking our answer from the last one to find this. This is a good two-step problem. You had to find the image distance so that in turn you could find the magnification. You know, we're blessed. The numbers worked out pretty good for y'all. Yeah, I'll show you what I mean. The numbers won't be maybe as kind if I do something like this and something else. We'll go to 140 on this. Give you all time to hunt down that equation. Five, 4, 3, 2, 1. All right. So if you did some good sleuthing, I'm not going to write. The givens are here. Great. I'm not going to write those out again. Step 2, magnification equals question mark. 3, magnification equals, and it equaled two things. It equaled the height of the image over the height of the object, which we don't have anywhere, and it equaled the negative. And this is where, if you made a mistake, I think this is where, the negative of the image distance over the object distance. So step 4, plug and chug. It's negative 2/3 over 2. Those 2's will end up canceling, those negatives will end up canceling, and you get positive 1/3. So, mathematically, you can get the answer. You can also realize that the answer should not be, I don't know why I have 3 twice in here. You can also realize a diverging lens always makes an upright image. A diverging lens always makes an upright image. Upright is a positive magnification. Upside down is a negative magnification. So, and again, this problem was kind of nice. If you'd accidentally done 2 divided by negative 2/3, you get the same answer. So that was kind of, well, let me fact check it. Nope, you do get 3. Never mind. If you got positive 3, it's because you got it in the wrong order. No, you don't get the same answer either way. So, let's go ahead and do the same thing. Basically, I'm going to copy and paste this problem. Boom, boom. And instead of it being the previous problem, we're going to go to the previous problem. So in the converging lens problem, go back to our answers. The object distance was still 2 meters, but our image distance was 2 meters as well. So we're going to have to change our answers here. Positive 2 and positive 2, what's our magnification going to be? Is it negative 1? Is it positive 1? Is it negative 4? Is it positive 4? So these were our answers from the converging lens had a positive DI and a positive DO. DO is always positive, so that's nothing fancy. What will the magnification be in this case for a converging lens? Well, we won't spend too long on this. We'll go to 1 minute. You've already hunted down the equation, so the math is nice and easy. 5, 4, wait a little bit, I see some people still thinking about it. I'll go to 110. And 5, 4, 3, 2, 1. Same exact process as last time. Same exact process. Basically, you know what? I say basically. I will. I'm just going to copy all of this and move it to the other slide because it's identical in terms of the setup. Now, my variables are different. So for step 4, my magnification is going to be negative 2 over 2, which comes out to negative 1. So the key takeaway here, and I think it's good I asked this because I got a bunch of different answers. Remember, converging lenses, generally, if your object is beyond the focal point, make an upside down image. So if my object was over here, my lens is over here, here's my focal point. This image is going to be upside down. Exact same size, that's just how the math worked out. Not always, but in this problem it ended up being that way. Exact same size, but upside down. A negative magnification means it's upside down. A positive magnification means it's right side up. Okay? Doesn't tell you where it's located, it just tells you that it's upside down or right side up. And it tells you the relative size. This is 1 times the size of the original. It's the same size. All right, let's go ahead and solve some more involved problems. That's kind of what we have left in class. A couple of these. I'll go ahead and show you all this. This is the last equation, and I hesitate to call it an equation because it's the exact same as the old one. I just say P equals 1 over F. That's the only addition. So we'll get to that. But at this point, we're basically just practicing these things. A 10 centimeter tall toy is placed 30 centimeters away from a lens with a focal length of 5 centimeters. What is the image distance, magnification, and image height if I use a converging lens? What is the image distance, magnification, and image height if I use a diverging lens? Seems like a lot, won't be that bad. All right, so step 1, what is given? We are given how tall the toy is. So that is the height of the object. That is 10 to the minus 2 meters. I really don't want to write 10 to the minus 2 every time, so I'm just going to put 0.10. Same thing. Sometimes scientific notation is better. In this case, it's not. Focal point is 5. And you know what? I'm going to be very careful here. I'm going to say for the convergent lens, the focal distance is 0.05 meters. For the divergent lens, since I'm writing all my variables for both steps in this, is negative 0.05 meters. Remember, negative for divergent, positive for convergent. Simple rule, but you do need to remember that, otherwise your answer will come way off. And the distance of the object in either case is always going to be, that's always a positive number, 0.30 meters. Now we will solve for all the things. We need to find image distance, di. We need to find magnification, m. We need to find image height, I. So this problem is really good because basically it covers the gambit of things I could ask you. It asks for all the things for a convergent lens. It asks for all the things for a divergent lens. I would not ask you a problem that has 6 possible answers. But this problem has a bunch of things because it lets you practice all the things, finding all the different variables. Step 3, we have our favorite equation ever, 1 over f equals 1 over do plus 1 over di. And what is simple equation? It's kind of beautiful. That's one of the nifty things in physics, in my opinion, is how you have such complex stuff going down, and it just boils down to such a simple thing, such a simple mathematical relationship. And because we know this, we can do so many things in life with it. I'll leave this for you all. I've already done this a couple times. But distance of the image is going to be 1 over f minus 1 over do. I subtract 1 minus do to the other side, and then 1 over everything. I'll leave that for you all to kind of go back and look at if you're uncertain how I did all those algebra steps. I've done it previously. That's a good exercise for you all as well if you want to practice your algebra. All right, so that's the distance of the image. Great. Magnification, we just did that, is going to be negative. Well, it's going to be hi over ho equals negative di over do. So if you want magnification, we're going to have di, we're going to have do, easy division. And we can use this part of it to then get the height of the image. The height of the image will just equal magnification times HO. Just some quick multiply HO over there. Great, HI equals that. So we're going to find magnification and then use that. So basically each step leads into the next step. We're going to get image distance. That's going to let us find magnification. That's then going to let us find the height of the image. These are great little exercises that can kind of go through and make certain you understand why I did each step, how this is a great algebra kind of stuff. Nothing crazy I did with algebra, but make certain you can kind of do this algebra and this rearranging. If not, you'll have a rough time on the final. So we then take all this, and we're going to use that for both of them, for the divergent and the convergent. Same exact equation. So I'm going to take all this stuff. The only thing that changes, only one tiny thing changes. The focal point changes from positive to negative. And because of that, all the answers will be different for the two cases. So when I'm doing my answers here, we'll do the convergent case first. And let's give myself a little bit more room. So we'll do the convergent case on the left, do all the number crunching there, then we'll do the divergent case on the right. Fingers crossed I can fit it all on this one slide. Converging. So converging, the distance to the image is going to equal 1 over 0.05 minus 1 over 0.3. Again, and the only rule that we needed to remember was that focal point's negative for diverging and positive for converging. That's the only rule we've needed to remember when it comes to positive and negatives. Everything else is just going to come out from the math. If it's positive, it'll come out from the math. If it's negative, it's going to come out from the math. So 1 divided by 0.05 minus 1 divided by 0.3. Make certain you plug that in your calculator the way it looks on the paper. And you get 0.06 meters. All right. One answer found. And we can check this. Our object distance was bigger than our focal distance, so we expect a positive image distance according to the rules that are previously listed. Great. One answer down. Magnification. And I'll write this again just so we don't forget what we're doing, equals negative distance to image over distance to the object, so negative 0.06 over 0.3, which comes out quite nice. This is negative 1/5, which is just negative 0.2. Even though I'm fairly confident in that, I'm going to plug it in my calculator because my brain's betrayed me before. Good job, brain. Not today. Magnification is negative. It's upside down. If you're negative, you get a right side up image. The negatives will either, because they'll cancel out in that case. And our last equation that we found was magnification is HI over HO. So if we multiply that HO over, we get the image. The height of the image will be negative 0.2. That's the magnification times 0.1. All right, this one I feel fairly confident in my ability to multiply. And we get a magnification that is negative 0.02. It is upside down, so it's negative. And it's 1/10 the size of the object. 2 centimeters versus 10 centimeters. So just a lot of simple algebra, a lot of simple number chugging. Nothing too crazy with our equations. Only thing remembering that divergent lens. Let's go ahead and start that one. The diverging lens, same equation, but my focal point is negative. That is the key here. The focal, you know what? Let's highlight that. Negative. This one was positive. So that's the only difference in anything after this. My image distance is going to get a different value, which means my magnification will get a different value, which means my height will get a different value, but it's all literally stemming from that one tiny difference. The equations are identical. Nothing fancy, nothing complicated here as far as if the first part made sense, it's more the same. It's just being careful with your calculator. And we get a much grosser answer, which is unfortunate, but I don't control these things. We get a negative image distance because it's virtual. Comes out to 0.043. With a bunch, it's way more gross. The number's not as pleasant as the last one. Magnification is going to equal negative, so we always put that negative in front, but then our image distance is negative, divided by our original thing. Negatives will cancel. And you get a magnification of 0.1433. It's positive, so it's going to make a right side up. And then my height of the image is going to be my magnification times the same thing. 0.1433 times 0.1 comes out to, just move the decimal place, 1 to the right. And we get an image that's a little bit smaller than the other one. There you go. So, like this problem a lot. I like this problem a lot because it kind of covers the full gambit of things I could ask you. Find the magnification, find the image distance, find the height of the image, and it kind of combines all the equations. And by all the equations, there's only 2 of them. Combines those 2 equations together. So, great problem. If you want to make certain you're good with lenses, this is the problem to do. All right. Next one, let's take a look at it, decide how much it's worth doing. No, I'm not going to bother with that one. It's more the same. I'm not going to bother with it. I'd rather get to the next stuff. I will solve this problem, post the solution. So when I post these slides, it'll have the solution to this one, and it all worked out. I'll let you all look at that. But it's more the same. It's not really worth the time and effort in class. I want to move on to powder lens. This is really interesting to me. I'll be straight up honest with you all. I did not know about this before a couple weeks ago when I was like, oh, I should include this in the lesson. But it's really easy. It's literally the exact equation that we've been working with. The reason I want to cover this, so it was in the OpenStax textbook. The OpenStax textbook is the one that actually connects to medical stuff. They have a whole chapter in the OpenStax about how lenses relate to the optics of the eye, and they talk about power, and I found this interesting. So I buy contact lenses. My contact lenses, so my prescription is negative 2.5. On the box it says negative 2.5. I never knew what that number meant. It's that. So whenever you all buy a box of contact lenses or glasses, and you get that positive whatever value, so if you are far-sighted, you'll get a positive value. If you're nearsighted, you get a negative. If you're nearsighted like myself, you can't see things far away, you'll get a negative value. That's the power. It is literally 1 over f. That's it. P equals 1 over f. So you can calculate the focal point of your all's lens if you wear contacts or glasses, if you want to know that. This is called diopters. What a fun name. The units of which you can get from this equation. It's just it's meters inverse. Focal distance is in meters. It's 1 over meters, so meters inverse. Diopters, so it's either negative 2.5 meters inverse or negative 2.5 d. Meters inverse diopters, I don't know why they don't put, well, they probably don't put meters inverse because most people would be very confused by that. So they just made up a new unit for it for reason, I don't know why. These can be positive, negative, and as I just mentioned, they explain all that. But literally, all we did is we had our equation before, and just in case you're not seeing, this is the equation we just used. It equals P. So 1 over F equals P. That's literally it's the same exact equation, just equals P. So 1 over F equals P. All right, so let's solve some problems with this because there's some fun things we can do with this. All right, an object is located at 2 meters from a converging lens. If the image distance is 4 meters, what is the power of the lens? Three-fourths D, that's diopters, 3/4 watts, 1/4 D, 1/4 watts. And I'm very confident that my right answer is up here, so if you get an answer that you're like, my answer's not up there, it's because you may have done an extra step that you did not need to do. All right, I'll go to 130, and then I'll leave it open and continue working through it. It's the last quicker question we ever have, so. All right, so I give you, step 1, I give you the object distance is 2 meters. I give you the image distance is 4 meters. I say, what's the power of the lens? Step 2, we are solving for power. And we have that equation, power equals 1 over F, which equals 1 over dO plus 1 over di. So we look at this equation, and we basically say, who needs the middle? Not us. We have object distance and image distance. So we just need to plug in 1 over 2 plus 1 over 4. If you did 1 over all that, you're finding the focal point. We don't want the focal point, we want the power. Power is 1 over the focal point. So, power equals 1 over 2 plus 1 over 4, which equals 3/4. And our units is diopters. What a fun word. I purposely put watts in here because we call this power, but this is not electrical power. The units for electrical power is watts. The units for optical power is lenses. Why do they use the same word? I don't know. Someone decided at some point, too little, too late. It is what it is. All right, so I will stop this in 3, 2, 1. Let's see how many people got it right. If anyone got it wrong, I know why. It's probably because it was online and there's a slight delay. So they get the answer in time. So sad. Oh well. So there you go. So there's a fun problem that I found. I like this problem in the book. And the book had the wrong information here. So there's some fun information in this problem. It says calculate the power of the eye when viewing objects at the greatest distance possible that your eye can see, and the smallest distance possible for an average 30-year-old like myself. I'm 29, I'm rounding up. With normal vision, assuming a lens to retina distance of 2 centimeters. So the size of your eyeball, roughly. So in the book, interesting enough, they put the smallest distance that you could see was 20 centimeters. So take your eyeball, go 20 centimeters away. It was saying that's as far as you could see. I didn't believe them because I could move my finger closer and be pretty in focus. So I did a little bit more searching. 11 centimeters seemed to be more on track. The more surprising result to you all, probably, is the statement that your eyeball can see things infinitely far away. And you may think to yourself, false. I can't see a human being infinitely far away. Correct, you can't. But that's not because your eye doesn't have the ability to focus that light. It's not your eye's fault. The reason is, think of someone infinitely far away. They're really small. So at that point, it's not that your eye can't focus on it, it's that the image that it would generate, like, imagine your back of your eye is a bunch of pixels, like, yeah, it's too tiny for a pixel. That's resolution. That's not your ability to focus, that's resolution. A better way to think about this is everyone in this room, assuming visual acuity, can see the sun. Everyone in this room can see the moon. The moon is really far away, but it's really big. So your eye can easily pick up objects far enough away, assuming that they're still big enough to see. They take up some percentage of your eye's view. So when we're talking about this, we're saying your eye's ability to focus light from infinitely far away. Yes, as things get infinitely far away, they become a tiny little speck. That's not limitations of your focal point. That's limitations of the amount of light that's coming from that object. That's the size of the object that we're concerned about. Here we're not talking size, we're talking ability to focus on things far away. So, just an interesting little, what's the word here? Distinction. So we can calculate the power of your eye's lens. So I told you my contact lens had -2.5. Your eye, remember, can change its power. So there's a range we're going to find here. We're going to find its ability to perceive things super far away and things super close, and that'll give us two different powers. So let's write down some stuff here. Step one, what's our first thing? One of our objects, our distance to our object is infinite. That's one case. So, and then our other object distance is 0.11 centimeters. Not centimeters, I've already converted it, meters. We don't care about the 30-year-old. That's not a variable we care about. Now, this next one, you may wonder, what is that going to correlate to? And if we draw a very awful picture of the eyeball, let's put something close by. Remember, what is the purpose of the back of the eyeball? What is it serving as? It is the screen that the image is being projected on. It is not the focal distance. The back of the eye is not where your focal distance is. If so, that would mean that all light that you're looking at would focus there, and that'd be very bad. It is where my little upside down person will be. Remember, your eye flips images, and then your brain kind of flips it. So, this lens to retina distance is actually the image distance. Both images, regardless of what you're looking at, regardless of anything you look at in the world, the image distance is from the front of your eye to the back of your eye, assuming you have it in focus. All right, so after this point, it's actually pretty straightforward. We're finding the power. We have two cases. We just said that power, yes, is 1 over f, which equals, I'm going to write the whole thing and just remind you all that if you have object distance and image distance, who needs the middle? If a equals b and b equals c, a equals c. So we don't need that. And then we just plug and chug. So the power for something that is infinitely far away, our image distance will be 0.02 plus 1 over infinity. And you say, what's 1 over infinity? And my answer to you is technically, you can't do 1 over infinity. It has to be 1 over the limit as it goes to infinity. So I'm checking that out there for those that know that, so you can feel good about it. If you take 1 and divide it by a really big number, it goes to 0. 1 divided by, put a giant number in your calculator. That is all infinite is. Infinite is a really big number. Does infinite exist in this universe? You all can decide that for yourself. That's kind of a philosophical question. But a really big number exists. Infinite's just a really big number. And if you divide anything by a really big number, if you divide 1 by a really big number, it basically goes to 0. You divide anything, you can try that for yourself. Do 1 divided by a really big number and you're going to get 0. Very, very close to 0. When compared to the other number, it approximately is. So, the power of your eyeball, when viewing things infinitely far away, is positive 50 diopters. It's a fun word. I enjoy saying it up here. We need more units that are fun. All the units that we've had so far, newtons, amps, ohms, none of them have a good mouthfeel. Haven't realized that till I've said diopters. So, some things just change you. All right, and the other one comes out to 59.1 diopters. So that's the power of your lens, that's the range of it, 50 to 59.1. Now the question, I guess one question that comes to mind is if you wear a contact lens that's negative 2.5, does it adjust these values? And my answer to you is, I don't know. I haven't looked into it. It's a great question. I don't know if you wear a contact lens, if you just add these two numbers and that's your new power. I don't think so, but This is the power of your eye. You can Google that and on optometrist websites you'll find that rough answer. So just kind of fun things. Now you know why that number's on your contact lens box or glasses box, or if you don't wear them and you do one day, then you'll know 50 years from now. God willing, we live that long. So that's it, y'all. That's everything in the course. How does that feel? Like, there's no new information. Yeah, isn't that nice? We did it, y'all. Yay! Physics. Woo! Physics 2 done. Everything after this point is going to be a review. So I'm going to start the note card. We have 17 minutes. Who knows how much I'll get it done. If I don't finish it today, I'll finish it on Tuesday. There's not really that much to put into optics. So let's go ahead and make a quick slide and kind of start just chucking the stuff in there. We may get it done in the next 17 minutes. We'll at least get some of it done. But at this point, y'all, everything's going to be review. Reminder, there will not be any clicker questions next week during the review. That is purely up to you. If you think it's more beneficial to be here for review, be here. If you don't think it's if you'd rather study at home and use that time for that, do that. I get paid either way. But because I do get paid, I will be here. Why is it struggling for slide size? Who can say? Not me. Well, because PowerPoint's not responding. Great. What's a lesson? We started with technical difficulties and we ended with difficulties. From dust we started and from dust we shall return. That's my lesson for this. All right. Great. I really don't want to have to redo all that, but hey, it hurt me and it felt my pain. All right, so let's go ahead and just start doing the note card for this. The great news about this note card, this last note card about optics, there's not that much that we've covered. So you're going to have lots of free real estate to put any extra information that you wish you'd been able to put on the other note cards, or have decided that you may forget and would like to include. So first thing we learned about, and by first thing I mean last week, we had electromagnetic waves. And let's make that a little tinier. Electromagnetic waves was the name of the last section. And we started off with saying that waves are made of two things, electric fields and magnetic fields. And we had a really simple equation that said that C equals E over B. C equals E over B, really simple equation. If I give you electric field, say you find magnetic field, done. And with this in mind, we also had the caveat, the very, very, very important thing that C equals 3 times 10 to the 8 meters per second in vacuum. Always, regardless of anything, this is the speed of light. Speed of light is 3 times 10 to the 8. And I'll put the in vacuum down here. And nothing, I almost want to put a giant star here. I'll erase it because it takes up too much space. Nothing can go faster. Nothing can go faster. And I say that with a little asterisk that, who knows? 20 years, 30 years, 50 years. I can't promise what the future discoveries will be. Our current understanding, everything I've taught you all in this class comes with the asterisk of our current understanding is this. Something I do want you all to take away from this class. Science is not absolute truth. Science is an observation of reality, and it's our best understanding of reality as it currently exists. You can take that to mean that our current understanding is absolutely perfect, but I'm sorry, you'll be disappointed. At some point, we learn new things and things change. Quantum mechanics basically taught us that a lot of things we understood weren't right. So, science is not absolute truth, but it is our best current understanding. It is based on evidence. It is based on reasoning. That doesn't mean throw it out. It just means that we can be wrong. Scientists can be wrong. Sometimes we can feel like scientists know everything and everything they say is right. It's probably pretty correct, but it could be wrong. And it's up to you to kind of investigate that. Generally, if there's an expert talking about something, they generally know more about it than we do, though, so it's usually good to trust experts. So don't chuck that out, but I did want to always kind of mention that. All right, we talked about waves. This is what the waves look like. We have wavelength, which is the distance between two identical spots. So if I pick the top and the top, there's wavelength. Wavelength, it's not the length of the entire wave, it's the length of between two identical spots, and we talked about amplitude. That's how big the wave is from the middle to the top or the middle to the bottom. Amplitude. Not from the top to the bottom, from the middle to the top or middle to the bottom. All right. And now that we've introduced these variables, we can introduce the equation C equals frequency times wavelength. Very straightforward equation, very simple. As C is a constant, as frequency goes up, wavelength goes down. Very simple, not too much to say there. C equals 3 times 10 to the 8. And then we also have the energy of a wave equals h times f, where h is Planck's constant. Do I remember Planck's constant off the top of my head? Nope. But let's go ahead and add that. That'll be given on the test. Planck's constant is h equals 6.626 e to the minus 34 with some disgusting units. It's not the worst units I've seen. Meters squared, kilogram over seconds. So the energy of a wave is strictly dependent upon the frequency. And so we have a nice little thing where I drew where I said we have frequency, we have wavelength, we have frequency, we have energy. As wavelength goes up, frequency goes down, and energy goes down. You know what? I'm going to do it the other way. As wavelength goes up, frequency goes up. So this is big, this is small, this is small, this is big. Basically, wavelength is the opposite of frequency and wavelength, or frequency and energy. As wavelength gets bigger, energy gets smaller. That's why that is why radio waves are not dangerous to you all. Right now, radio waves are passing all through your body. Cell phone signals are passing through your body. Wi-Fi signals are passing through your body. Hopefully everyone here is feeling okay. If you're not, I'm sorry. But it's not due to the radio waves. It's due to other factors. Now, you get hit with some X-rays for a long period of time, you get hit with some gamma rays for a long period, short period of time, yeah, then you're not going to be having a good time because of those. Those have a very high frequency and a very small wavelength. So, there's that. Few equations, nothing too bad. Notice I did not put intensity up here. Why? Because I'm not going to test you on it, so you don't need to know it. Intensity was the one that had the mu naughts, the E naughts, all the naughts. So don't worry about that. It's not going to show up on the exam. We did see it in the discussion. There was like one problem in the other thing. So there you go. There is electromagnetic waves. Let's go ahead and do a little corner on reflection. It only needs a little corner. Reflection, angle in, the incident angle equals the reflected angle. What comes in? So if I have a flat surface, light ray comes in, boom, 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 boom. If this is 30 degrees, then it bounces off with 30 degrees. If you know how a bouncy ball works, you know how light works, as far as reflection is concerned. Now, that surface, maybe it's a little curved. You remember, you take the technique, put your pencil on it, that's the area vector, and it's symmetric about that. So that little dotted line I drew is my area vector. Great, there's reflection. That's literally all you need to know about it. It acts like a bouncy ball. We then talked about refraction. That's what I showed you all in the little simulation today. So for refraction, we introduced the idea of this index of refraction, which is C over V. This has no units. There's no units because C is meters per second, V is meters per second, so they cancel out. And so N is greater than 1 always because C is greater than V. Always. Always. If the light travels faster than 3 times 10 to the 8 in some material, then you've broken the rules of physics and you can go get your Nobel Prize and whatnot. But that's not going to happen. I mean, if you do that in the test, yeah, sorry, that's wrong. If you find a material that has an index of refraction less than 1, you should really double check your work. If you do this in the real world, you should really, really double check your work because you would be very, very famous. Very, very famous. Be a big deal. N1 sine of theta 1 equals N2 sine of theta 2. That's Snell's law. We'll draw a beautiful little picture where N1 is the material here. Theta 1 is that. And then it's going to reflect depending upon, that's theta 2, that's N2. This is what would happen if N1 was greater than N2. The angle will be bigger. I will repeat the exact same picture. You can decide whether you think this is worthwhile and put it on yours. So that goes with that one. If N1, N2. If N1 is less than N2, the second angle is smaller. So I'll zoom in on all that since it's a little small. So the incident angle, oh, I hate that, this zoom works. All right, I said I'd zoom in, but what does that do? All right, there's only so much I can zoom in before it doesn't let me move around. So the exit angle is bigger if I'm going to a less dense medium. The incident angle is smaller if I'm going to a more dense medium. Remember, the more dense it is, the bigger the N, the smaller the velocity. Yeah, and we're going to be able to finish this in 6 minutes. That's how little we've actually covered. In terms of like the things you need to know, it's really not that much. It's only been 2 weeks. It makes sense. So refraction, let's put a little box around it just to keep it nice and its thing. So we'll quickly talk about lenses. I'll draw some pictures. I'll put the 2 equations we covered. That's it. That'll be it. That'll be everything that hasn't been on test 1 or test 2. Not a ton, but enough. Enough that I'm happy that we were able to actually cover some optics stuff. Oftentimes in Physics 2 classes, optics is just kind of tacked on in the last week and kind of crammed in there, and we don't really spend any time on it because we don't have time for it. But I'm really pleased with how it's turned out this semester and that we've been able to actually learn a little bit about optics. We did not cover lasers at all. If you go and get a physics PhD, you also won't learn about lasers at all. I don't know why. They don't teach you about lasers in any of your physics classes, unless you're specifically doing research on lasers. Then yes, you take a bunch of classes on it. But please, look into lasers. They're really interesting and really useful. There's some really good videos on them out there. I'm starting to learn a little bit about them myself because they just happen to pop on my YouTube feed. All right, let's quickly draw a convergent lens, divergent lens. So, lenses. I'm just going to put our equations down here. These are the 2 equations. We have magnification is HI over HO, which equals negative DI over DO. And then we have power equals 1 over F equals 1 over DI plus 1 over DO. And, we'll put a little rule here. Positive for convergent lens, negative for divergent lens. Look at that. That's it as far as equations are concerned for this week. I'm just going to draw some quick pictures of lenses up here. So a convergent lens. If we have our focal point here and here, oh, it's so hard to draw straight lines. We're going to see how I do here. I wish I had a ruler. Remember our first rule was that the light comes in. Let's draw these with 3 different colors. You're going to see how bad I do when these lines don't really come together the way they're supposed to. So light comes in, and then it passes through the focal point. That's line 1. Line 2 is that it passes right through the middle. And great, you're like, wow, those came together. My third line, I have no hope of it coming together because I'm sure I did not draw these perfectly. Line 3 passes through the, oh, look at that. If I just fudge the line a little bit, wow, look, they converge. Where they converge is where the image is formed. And I'll make a new F here because it kind of got destroyed by my beautiful lines. So my new image, there's my object, there's my image. Where they converge is where the image was generated If you draw those lines really nicely, it turns out perfect. Mine are a little fudged. It's hard to draw straight lines on this thing. But you're not going to have to. I may ask you a question, which of these is roughly correct? And you saw a couple of those in the clicker questions. So you can expect, at worst, something like that. Here's my divergent lens. Same focal point. If this is my object, I need the first one. The first line is going to go straight. And then it's going to be as if it passes through this focal. How much it goes up, we kind of draw a dotted line and draw it straight up like that. The second one, super easy, just goes right through the middle, and then I squiggle it. Oh, I hate drawing straight lines in this thing. In my high school class, I literally get a ruler and put it up on here. All right, and the last one passes through the focal point and then goes flat. And these, see, you can see how bad it is. This one should go, woo. I'm going to redraw the second one. All right, now I feel like I did something weird here. All right, let's just stick with those two for now, because why? So it's trying to head towards this one, and then it goes flat. So that was my mistake. There you go. That's it. Done. That's all you really need for that. And even for this picture, I really recommend that you all just find one online, print it, kind of glue it to your thing. Like, you're welcome to draw these things, but it's easier to just find a picture online, glue it to your all's note card. Heck, take the one out of my slides. I don't care. At the end of the day, you need to know that convergent lens, the lines converge to make an image that's upside down that you can project on a screen. And the other one, these lines kind of come together at this point, and we get, there's my image. It's where we imagine that those lines are kind of coming from. If we pretend that those lines coming from the right came in a straight line, that's where they kind of converge together, but they don't really. All right. Well, man, I will be here next week. We'll have a great time reviewing. I will send out a poll sometime tomorrow, probably, just asking what questions, what concepts you all are having the most challenge with, and attempt to incorporate those into the review as well next week. So, outside of that, if you have anything burning that you want me to include, just shoot me an email. Or anything you have questions about. Nearing the end of our precious time together. In 2 weeks will be the last time we see each other. How sad. Well, maybe. I don't know. Maybe I'll see you in Publix or Walmart or something. I don't know where you shop. Have a good one, y'all. If you have any questions, come on up.